When you hear YoloV5, you probably think of object detection, right? Drawing bounding boxes on the objects. But what if I told you it can also perform image classification as well as the segmentation? We saw YoloV5 architecture in detail in the last video, but that's actually for object detection. Now let's break down the architecture for segmentation and also for classification tasks. We'll also look into how YoloV5 learns these segmentation tasks being a one-stage network, and also what kind of loss function is used for this segmentation task. Okay, let's start. Segmentation means classifying every pixel, right? Instead of drawing only the bounding boxes, you just get the contour of every object. So the shape boundary is precisely predicted in the segmentation, right? So you can see here we are getting the exact shapes of these objects. This is called segmentation. But there are many types of segmentations. This is semantic segmentation and this is instance segmentation. What is the difference? If you look at the image, there is one dog and three sheep, right? In case of semantic segmentation, it gives the mask for each category. That means it gives one mask for the dog and one mask for the sheep. It doesn't matter how many sheep are there and where they are located. It gives a single mask for all the sheep because this is at the semantic level. That means category level. It's not the instance level. But in case of instance segmentation, each sheep is considered a different object and there will be masks separately predicted for each sheep. Okay. So we have three different masks for three different sheep here. How do I get this separation? This is very simple. Concept wise, instance segmentation is a combination of semantic segmentation and then object detection. In case of semantic segmentation, we are getting the mask. In case of object detection, we are getting the boundary for each individual object. If you combine these two concepts together and then give it as the output, that will give me the instance segmentation. Okay. So that is the concept. So instance segmentation provides unique mask for each and every object. So YoloV5 actually does instance segmentation, not semantic segmentation. There are some popular methods like Mask-RCNN for instance segmentation. This is the architecture of Mask-RCNN. It's a two-stage network. It generates the feature maps and also it generates the proposals separately using the RPN module. And finally, it actually combines them to get the final bounding box predictions. Similarly, it predicts the masks also on the proposals. So what are proposals? RCNN models have a module named RPN, Region Proposal Network. This module predicts the possible bounding box coordinates. If you see here, these are all the possible bounding box coordinates in this particular image. So the region proposals are actually the possible bounding boxes. For example, in this image, there are two objects, right? So in case of RPN stage, it actually predicts multiple bounding boxes, which can be the candidate bounding boxes for these objects. Then RPN actually gets the feature map for only those bounding boxes. And then those are passed to this fully connected layer for bounding box adjustment and the category prediction. Similarly, these feature maps for those objects, for those proposals are passed to the mask branch for the mask prediction. So it's easy for Mask-RCNN to give masks because we already have the bounding boxes from the RPN, which are region proposals. And for each proposal, you can actually predict the mask. So the mask prediction happens at instance level for the Mask-RCNN. But how to do this in case of YOLO? YOLO is a single stage detector, right? That means there is no RPN for getting the proposals. So there are no proposals. We predict the boxes and the categories in a single shot, direct prediction. So the masks are also needed to be predicted along with the bounding boxes. So predicting the mask at instance level is difficult task here. It's not straightforward. Hope you understood the problem. Because we don't have RPN proposals, it is difficult to predict the mask at the proposal level because we don't have proposals. So instance level mask will be difficult for us. So let me clarify if you have some confusion. This is the Mask-RCNN architecture. And here the RPN gives these bounding boxes. Now I know the object locations in the image already, right? Based on these bounding boxes. I just need to adjust these bounding boxes and predict the categories here. The feature map coming from this, right? From the RY pooling step is actually a feature map for individual proposals. Let's suppose the RPN predicted 1000 proposals here, right? Here you got 1000 proposals. This particular feature map will have individual feature set for the 1000 boxes. Okay. So this is done by using this RY pooling concept. I'm not going detail into this RY pooling, but the core idea is we get the feature maps at the object level or instance level here. And these feature maps are used in the mask branch for predicting the mask. But in case of YOLO architecture, there is no RPN, there are no proposals. We are predicting the bounding box coordinates and class probabilities directly from this feature map. And this feature map is of the whole image. It's not for a particular object. It's for the whole image. Okay. So predicting the mask at the object level or the instance level is difficult. So what should we do? First of all, let's think about what can we do here. With this architecture, what can we do? We can get the masks at the global level, right? These are the global features. Then we can get some kind of mask at the global level. Some kind of mask which represents all the objects available in that image, right? So based on that idea, can we create the masks at global level, which is kind of representative masks for all the objects, and then separate the objects somehow? Suppose you get this global mask like this. Okay, this is the global mask you are getting. Let's call this as prototype. Okay, can we do something on this to get the mask like this? If you see here and here, this is a global mask, whereas this is individual mask for objects. Can we do something on this to get here? Think of what needs to be done to get from here to here. First of all, what are the problems here with this particular mask? The mask is not proper, right? There is no sharp boundary and there are a lot of background also coming into this, right? The area here is not completely 0 and the area here is not completely 1. It's not like a binary mask here, right? So we need to modify this mask to get all the zeros here, or at least closest to zeros here, and to get all high values here for the objects, right? That's what we need to do. So we need to add some kind of weightage for each and every pixel here, more weight for this region and less weight for these regions, so that this region will be, the object regions will be enhanced and the background region will be nullified. Okay, that's what we need to do. So let's call them as some kind of coefficients. Now after that step also, I will get a single mask for all the objects, right? But I need separate masks for both the objects. I need a single mask for dog and single mask for cat. How do I get that? The first thing I can think of is crop the mask based on bounding boxes. We are already getting the bounding boxes from the detection head. Why don't we use that bounding box on this particular feature map and crop this portion as a mask? That's a very simplest thing to do. So we can improve this mask region by using some kind of weighting factors or some kind of coefficients. By multiplying those weighting factors to this mask, you get a better mask. That's the idea. And once you get the better mask after multiplying with the coefficients, you crop this mask based on the bounding boxes you get. Then you will have separate masks for both the objects. So let's put our thought process, whatever we have discussed so far, into a flowchart. First, we need to get the mask prototype from the global features, right? Let's say this is the mask prototype. Then apply some kind of coefficients to get better masks. So let's call them as object level coefficients or mask coefficients, whatever you call it. Coefficients I am saying here because these are some kind of weights. By adding some kind of weight factor to each and every pixel here, you are able to convert this into these two masks. And I am mentioning here object level because I need to highlight these object level regions separately for both the objects. Let's assume that you are learning these object level coefficients somehow. And using those coefficients, you multiply this mask with these coefficients to get the object level masks separately. Okay. Still we see some area here which is of cat, some region here which is of dog. But I need only the mask for dog here, only the cat mask here. How do I get that? Let's crop the masks using bounding boxes, right? So if you crop the masks using the bounding boxes, we get separate masks like this. This is the idea. So are you convinced with this idea? Will this work? I'm not fully convinced because the mask prototype which is coming here, it's not proper. How can I get this mask into these or these like this? This step is very easy. Once you get this object level masks, that is very simple. But how can you get this into these two masks, right? It is looking very generic here. It's looking like a feature map. It's not looking like a mask here. So what should we do? Instead of taking one mask, let's take two masks. If I predict two prototypes here, you can see we are able to get better prototypes. These are not modified by me. Okay, this is not something modification from the previous image. These are actually generated from the model during the prediction. So if you can generate two mask prototypes, there are chances that you will get these kind of mask prototypes, which are much better than your previous case. So what should we do? Should we stick with only these two prototypes? Here there are only two objects, so that is fine. What if we have more than two objects? And you can see some background here as well. Even these prototypes are not perfect. So let's increase the prototype and see how it works. Now the prototype increased to 4. These are even better, right? If you look at this, this has almost removed the complete background. This is able to capture only the foreground part. And these two are for separate categories. So if you increase more and more prototypes, the prototypes tend to be better, right? So I can merge these four to get these definitely, right? It is comparatively much easier now to get these kind of object level masks from these prototypes, right? So the idea here is create more prototypes so that it's easy to eliminate the unnecessary portions and get better masks. Okay. Now let's think how to implement this. You understood the flow, right? What should be done. Now how to implement this? I can get these prototypes from the feature maps. Either it can be from the backbone or neck. Usually neck will be better because neck will have better features. So we will predict these prototypes from the neck part, which is our path aggregation network. Okay. Now what are these object level quotients? Let's call them as mask quotients. So how do we get these mask quotients? When we say object level quotients, these should be learned at object level, right? That means detection head. So let's learn these in the detection head. We already have the classifier and bounding box prediction in the detection head. Let's add these mask quotients also as a separate branch. Okay. So we are good with this. There is no learning happening here, so you need not to worry. This is just a cropping part, post processing. Okay. Now combining these two ideas like learning the prototypes from the neck part and object level quotients or mask quotients from the object detection head part. Combining these two ideas, does our idea look like this? Is this what we have discussed so far? Let's go this step by step. This is the backbone and this is the neck part, right? We need to predict the prototypes, which are these, from the neck. So from the neck, we are taking the feature map and passing to some kind of network, Protonet, and then getting these prototypes. This is one. Now in the second path, from this neck, we are going to detection head or prediction head. In this prediction head, along with the classifier and the bounding box prediction, we are predicting the mask quotients. These are actually object level, object specific quotients, which are called mask quotients. Okay. We are getting the prototypes here and we are getting the mask quotients here. Now in this image, there are two objects. One is the person and second one is the racket. So two outputs should be coming from the detection head. So for the two objects, we are getting two mask quotients. Okay. So the first one is for the person, second one is for the racket. Remember, these are actually mask quotients. These are not the actual masks. Okay. These are only quotients here. The prototypes are here and the quotients are here. The prototypes are 4. So for each detection, for each object, there are 4 quotients here. You can see 4 values. So for simplicity, let's assume that these are just +1 and -1. Wherever you have plus, it is actually +1 and this is actually -1. As there are 4 prototypes here, you should have 4 values here in the total. So these are considered as quotients, right? Which are weights, similar to weights. So if you look at the prototype here, the person is more prominent in the first 3 prototypes and the last prototype doesn't have person. So if you want to create a mask for person out of these prototypes, I should give more weightage for the first 3 values and less weightage for the last prototype. That is precisely it is being done in the mask quotients. So the first 3 prototypes, it is +1 and next one it is -1. If you see that operation, it is happening here. It is addition of the first 3 prototypes minus the last prototype. You get the person mask like this. And similarly for racket here, it is more prominent in the second and fourth prototypes, right? And it is not visible in the first and third prototypes. The same thing if you add it as a weight factor here, the quotients are +1 for the second and fourth prototypes and the quotients are -1 for the first and third prototypes. And the calculation goes like this. So this second prototype and the fourth prototype should be added together and subtract with the person prototypes. Then you will get more prominent regions for the racket mask and for person there will be lesser values. So if you see both of these masks, you still have some portion of racket here and you still have some portion of person here. But only thing is their significance or weightage got reduced, right? How can I get rid of these values? After you do this multiplication, so this total process, whatever we have discussed, it is happening in this one. Protonet outputs, which are prototypes, are going here. At the same time, these mask quotients are coming via NMS and coming here. Here we are doing this multiplication with the quotients as well as the prototypes. And whatever output you are getting, these are actually these two masks. Now these two masks, I need to crop to get the object specific mask. So first I have the person bounding box. I will crop from this mask to get the person bounding box here, which is a person mask here. And similarly for the racket, it happens the same way. Now the masks look like this. For person, it looks like this, and for racket, it looks like this. Now apply some kind of thresholding, okay, to get the mask as binary. That means 0 or 1, right? So if you apply some kind of thresholding, the higher values will be existing, and this racket which is having the low values, that can be eliminated. So we can get the binary mask by applying this threshold. That's it. This is the whole idea of mask prediction. Okay. You predict the prototypes and you predict the quotients. You somehow merge these two to get the proper mask here. And then after that, you get the object specific mask by cropping with the bounding box. And then thresholding gives you the binary mask. If you understood this far, the total concept, congratulations to you. We can actually publish a research paper on this. But sadly, someone else did already. This is nothing but YOLACT paper, which is you only look at quotients. You only look at the quotients. So don't worry about predicting the instance masks. Instead, predict the prototypes and the quotients properly so that you can create the instance mask from these prototypes. In this whole idea, predicting these quotients is actually critical. Getting these prototypes are actually comparatively easy. The whole idea we discussed so far is from this paper, and this is the block diagram of this paper. This is the paper and it got released in 2019. So far whatever we have discussed, it is predicting the instance segmentation masks for a single stage object detection network, just like YOLO. So what did YOLOV5 do? Simple. They incorporated this idea into their network. Just you replace this part, which is the backbone and neck, with the YOLOV5 backbone and neck. Just you replace this part, that should be good enough. This total prediction mechanism of mask is exactly the same as YOLOACT paper. Okay, it's as simple as replacing the backbone and neck. And of course, they have added this mask quotients branch in the prediction head. Now we need to understand two things here. The first thing is what is this Protonet architecture, and the second thing is how these mask head are added to the existing prediction head and how actually it works. These two areas we need to focus. So let's have a look at the block diagram. This is the block diagram of YOLOV5 for the segmentation task. Don't worry, this just consists of backbone and neck. This part is backbone, which is our darknet 53, and after that you have spatial pyramid pooling, and then this total thing is your neck, which is path aggregation network. Okay, so this path aggregation network is actually the same as your object detection, just only minor changes are there. If you see carefully, this is still a two-path network. First path goes like this, and then it comes back like this in the second path. Only for the visual representation, I kept the blocks vertically. Otherwise, it is actually one top-down and bottom-up approach. Two paths, that's it. It is exactly same as your path aggregation network. Only difference is, in case of object detection, path aggregation network has C3 blocks, just like backbone. But here for segmentation, they have removed those C3 blocks and they have added more convolution layers and residual connections. Okay, that's the only difference. They removed these C3 blocks from path aggregation network, and then they have added these more convolution blocks. Now, if you see this, from the neck, we are getting 4 outputs, right? If you remember, we need to get the mask prototypes from the neck part, right? So from this neck, from the path aggregation network, we are passing the features to the Protonet architecture, and inside this Protonet, it will predict the prototypes. Then apart from this, there are 3 outputs going to 3 detection heads. This is same in case of object detection as well. Okay, so 3 feature maps coming out of the neck part, which are going as input to the detection head later. First, let's have a look at the Protonet architecture. It's very simple architecture. It just has 3 convolution layers. That's it. This is the Protonet, right? The input should be coming from the neck, which is path aggregation network, and the output should be these prototypes. So if you see the neck output, which is 128 by 80 by 80, this is going as input to the Protonet, and it has 3 convolution layers. The first convolution layer doesn't change anything. The feature map output is still the same. Next, you have the upscaling layer, which is actually changing from 80 to 80 into 160 by 160. Okay, and then later you have 2 more convolution layers. The final convolution layer converts from 128 channels to 32 channels. So if you look at the output here, it is 32 by 160 by 160. So we are actually predicting 32 mask prototypes. In this example, we saw only 4 prototypes, but actually in the network, we are predicting 32 mask prototypes. Okay. And this 160 by 160 is actually the size of each prototype. So each prototype here, this is of size 160 by 160. Okay. After performing multiple experiments, they identified that 160 by 160 is best. How it is decided? It is simple. It is just 1/4 of your original image resolution. The original image resolution is 640 by 640. If you divide by 4, you will get 160 by 160. So whatever your input resolution is, mask prototypes will be of 1/4 size of the original input. This is the Protonet architecture. It's very simple architecture, only 3 convolutions. Okay. Now let's have a look at the detection head, because we have mask quotients coming from the detection head. So this is the detection head. This also looks exactly same as the case of object detection. Only difference is here in object detection, you have only 3 branches. After this splitting, you have only 3 branches, one for XY coordinates, one for WH, and one for the categories. Whereas you have one more in between here, which is of 32 dimensions, because we have 32 prototypes. This particular branch here is actually for mask quotients. So this 3 by 80 by 80 32, this is predicting the mask quotients for 32 prototypes. Same thing here. This branch is for mask quotients. This branch is for mask quotients, 32. All these 3 branches are performing the same operation, only your input feature maps are different. Here the feature map is 80 by 80, here the dimension is 40 by 40, and here 20 by 20. Otherwise, it's the same operation happening in all the 3 branches. Okay. And if you see here, the only difference is one additional parallel branch, which is of 32 prototypes. Okay. That's why here it is 117. It's not 85. In case of object detection, here the value will be 85, out of which 32 goes for the prototypes. Okay. And from all these 3 heads, you are getting the feature maps, and then you concatenate here. This final output goes to NMS and post processing. Same as your case of object detection. So this is how the prediction head looks like in case of segmentation. Only addition is you have a parallel branch, and the dimension is of 32 because you have 32 prototypes coming from the neck. This number should match with the number of prototypes. Okay. Now we understood how Protonet looks like and how these mask quotients are getting predicted in the prediction head, right? Let us look at the loss function. For learning these masks, we should have a loss function, right? So let us have a look at that. First of all, what is the target of this mask prediction? Target means ground truth. What is the ground truth of this? Ground truth should be object-wise binary mask. This is a binary mask, 0 and 1, 0 and 1. These are object-specific masks, right? Then what should be the prediction? Prediction is our final object level mask. Prediction is not prototype. Prediction is not the quotients. Whatever you are getting after doing all this process, whatever the output you get here from the prototype, you are getting the object specific mask using these quotients, and then you are again cropping based on the bounding boxes to get the final mask, right? So that final mask which is coming from this block is the prediction from the network. So that should be given as the input to the loss. So both the inputs, one from the ground truth and second one from this prediction mask, goes to this loss. And the loss used here is binary cross entropy loss because it's binary. You need not to worry about the category here. You just need to predict whether each pixel belongs to foreground or background. That's it, right? So only 2 categories. So binary cross entropy loss is used for mask prediction here. So hope you understood the whole flow for mask prediction in case of YoloV5. Now let us look at the code walkthrough. I will show you the code where this whole processing is happening. This total process, right? How these are happening in the code, we will go through it now. So if you look here, this is the tutorial Jupyter notebook I took from the YoloV5 repository. They have released a tutorial notebook where you can directly start doing the prediction. So for understanding that whole mask prediction process, I ran this tutorial and I saved the intermediate outputs. Okay. So this is just importing the library, and then using this YoloV5 X segmentation PyTorch model, I am predicting on the image. This is the image. This image is what we have been seeing in the example. Okay. Where you have one dog and cat. On this image, I am doing the prediction. When I do this prediction, the final output will be saved, right? So if you look here, this is the final output I am getting, which is being saved into this particular folder. This is the final output. Now these are proper masks, right? We can see that the masks are very good. But I want to understand what are those 32 prototypes we are saving? How do they look like? And after doing this quotient multiplication, how they convert into object specific masks and how do they look like? and where that operation is happening in the code. And finally, after cropping, how do they look like? So all these intermediate stage outputs I want to verify. So for that, what I have done is I went to this predict file where actually the prediction is happening. So this is where the prediction is happening. If you see whatever data set I have passed, whether the image or video, it will come here. It will go through one by one images and it pass through the model. This is where the actual inference is happening. If you look at the model, the output we are getting two parts. One is the predictions. These are coming from the detection head, the output from the Protonet. These are actually your prototypes. These two outputs are coming from the model, right? Now what we are doing here is I want to save these prototypes. These prototypes are 32, right? So I want to save these 32 prototype masks properly, right? So I am going through the loop here and then taking those prototypes, converting into NumPy, because these are actually PyTorch tensors, converting into NumPy array, and then changing the range to 0 to 255 for better visualization. And after that, saving into a PNG image. So all this is actually for saving the prototypes. 32 prototypes are being saved using this logic. Now let us have a look at those prototypes once. These are the prototypes which are 32 predicted from the Protonet. So if you look at the prototypes, each prototype concentrates on different areas of the image. If you look at this prototype concentrated on the right hand side. This concentrated on the left hand side of the image. If you look at this concentrated on the background portion, completely eliminated the foreground objects, right? Whereas if you look at this particular prototype, this concentrated on the foreground, it has eliminated the background. Like this, each prototype gives different types of activations or different types of enhancements. Okay. So these are the prototypes coming from the network for my input image, dog and cat, right? Next, after saving these prototypes, what are the predictions we are getting? Those are actually classification, bounding box prediction, as well as mask quotients. All of them will go to non-maxima suppression and you will get the final objects. You have only two objects in this image. So this output prediction should have only two objects. Now we will go through a loop here again. For each detection, we are doing the mask processing here, right? So in case of retina mask, it will go here, but by default retina mask is not being used. So it will go to this one. If you look here, proto is going as one input. Whatever the prototype you got, that will go as one input. And next thing will be your mask inputs. So both will go to this process mask. In case of process mask, what we are doing is this multiplication. This is the main thing you need to look at. Whatever the mask quotients are there, those are these masks in, and the prototypes are these. These two are multiplied together to get the final mask. This mask should be object specific mask. Now I want to save those also. I know that there are only two objects. So these quotients will have only two elements, right? So if you look at this, the quotient's dimension is n by 32. N means number of objects. So this will be 2 by 32 and the prototypes are 32 by 160 by 160. After doing this multiplication, you will get 2 by 160 by 160. So only two masks will be there, which is the output of this. Now these will go through this for loop. And in the same way like we plotted earlier, I am plotting these processed masks. So these masks should be object specific masks, right? Let's have a look at those. These two are actually the object specific masks. These two are the output of your multiplication of prototypes with the mask quotients. After you multiply prototype with the mask quotients, you get this kind of output. Okay. And after this step, you are doing the cropping based on the bounding box, right? Let's see that. After doing this, you are downscaling the bounding boxes because these boxes are of 640 by 640 resolution, whereas mask is of 160 by 160. Now I need to crop this. Okay. Whatever mask you are getting, based on these bounding boxes, you are cropping those masks and getting only the object specific mask. Now here I am saving those again. Two objects are there, two masks should be saved here. Those look like this. These two are actually cropped masks. Once you cropped, this portion will go away, whatever I have showing here. And the same way this dog portion will go away. So after cropping, these are the final masks which I am getting plotted on this image. Okay. These two final masks are being plotted on this particular image. So this is the total process happening inside the code. Basically from the model itself, you are getting two outputs. One is the detection head and one is the prototypes. And you are using both of these to get the final masks by doing some processing. And we saw what exactly the processing is happening. Okay. Now let us look at the loss function. The loss function which is used is actually binary cross entropy. This is what I have mentioned. binary cross entropy. Now for this, two inputs should be going. One is your ground truth mask, which is like binary mask, and your prediction mask. Prediction mask, again, we should do the same process for calculating, right? You have the detection head, which is your mask quotients, and the prototypes. Both of them you multiply together and you will get the prediction mask. This prediction mask and the ground truth mask will go as input to binary cross entropy loss. So this is how the loss function is implemented for the mask head. Fine. So hope you understood how the whole process is happening, from getting the prototypes and the mask quotients till getting the object specific mask or instance specific mask. And also we looked at the loss function. Now coming to the architecture I followed the same method as previous. I took the pre-trained weight, I downloaded from the YoloV5 repository, and I converted that weight into ONNX format here. After converting into ONNX, I actually visualized that using Netron. Using this visualization tool, I'm able to visualize the whole architecture, and from that visualization only, I draw the block diagram, which we saw in the slides. This is the block diagram I got after doing the Netron visualization. This is the network. Input is 3 by 640 by 640, and you have few bottleneck layers, CSP layers, and then after that you have SPPF, where you have max pooling and then concatenation, and from this it will go into different paths. Okay, and if you see here, this one output coming from this is actually your Protonet. Okay, this particular block is actually Protonet. 3 convolutions and 1 resizing. Resizing is actually upscaling. If you see, it starts with 80 by 80. After resizing, it gets to 160 by 160. And from the final convolution layer, you have 32 by 160 by 160. So this we saw in the last object detection itself, that sigmoid and then multiplication. This is actually the implementation of SILU activation. Okay. When you say convolution, it has convolution, batch normalization, and SILU activation. Okay. So this output, whatever you are getting here, this is actually your Protonet output. That means 32 prototypes are coming from here. Okay. And then it will continue, and you have 3 detection heads, and each detection head will have 117 elements. Okay. And 117 will be splitted into 4 parts now instead of 3, because 2 parts are for X, Y, and WH. And this one part is of 81 dimensions for categories. And then you have 32 dimension channels. This is for the 32 prototypes. Similarly here 32, 20 by 20 by 32. Similarly here 80 by 80 by 32. So one parallel branch here, which is our mask branch, okay, which is having the dimensions as 32 dimensions in the end. This is for predicting the mask quotients. So this is how the architecture looks like. So whatever the block diagram I showed in the slides, I created that block diagram using this architecture. And this architecture is for YOLO-V5 okay, small version. Because you can see this is for YOLO-V5 segmentation model. This is what I have plotted over there. Depending on whether it is yes or medium or large, based on that, your number of bottleneck layers here, how many bottlenecks are there, how many C3 blocks are there, those will increase. That's it. Okay. So this is how the architecture looks like. Now we understood how YOLO-V5 can do instance segmentation, right? So far we have discussed about instance segmentation. Now let us look at the classification. Classification is a very simple task compared to object detection and segmentation, right? So this is the architecture for classification. Okay. It's pretty simple. Just remove all the neck part and detection head, everything. Just keep only backbone. Only backbone is enough for the classification. So this is just your CSP.NET 53 with the C3 blocks. So the number of this 4, 8, 12, these indicates your number of bottleneck layers. This you can tweak however you want. This also will be different for various versions of models. Like YoloV5 small will have different numbers here. YoloV5 L will have different numbers. YoloV5 X will have different numbers like this. So you can change accordingly. But the input is actually 224 by 224 going here. And these are your number of channels at each layer. So input channels are 3, output channels are 80. Input channels are 80, output channels are 160 like this. It goes through multiple convolution layers as well as C3 blocks. The only area you need to focus is this adaptive average pooling followed by linear layer, which is your fully connected layer. Adaptive average pooling is for converting this feature map into a single dimensional vector, because we are using fully connected layer for the classification, right? If you use fully connected layer, the input it expects is a single dimensional vector. Here, this fully connected layer is expecting a dimensional vector of 1280, right? So this adaptive average pooling takes this convolution output and then convert into a single dimensional vector of dimensions 1280. It's actually average pooling. Okay. So this 1280 dimension vector will go as input to this fully connected layer, and this fully connected layer will give me the output as 1000 categories. So this dimension is 1000 because it's for ImageNet dataset. Okay. If you are training the model for your own dataset, you need to modify this fully connected layer. Let's say you have only two classes here, dog versus cat. Then this layer will be 1280 by 2. Okay. So that's all. This is how YOLOV5 model is adapted for classification and segmentation tasks along with the original object detection task. Hope you learned something from this video. Thanks for watching.